Key, and this is my signal noise analysis project. So for part one, our scope was to take the noisy audio and the clean audio, and we're going to both visualize them and plot the fast Fourier transform to understand where the specific noise frequency is coming from. And that way we can isolate it and then basically cut it out of the noisy signal so that we can receive our original signal back as best as possible, even though we've cut out some of those frequencies of the speaking audio as well. So this is the original audio.
Ice cream is delicious. Milk chocolate is not.
So as you can tell, it's pretty crispy. This is obviously without any noise, and then this one will be the noisy audio.
Ice cream is delicious. Milk chocolate is not.
Okay. So this is the plot of both of them, and you can see that the noisy audio consists of thicker portions where he's not speaking because there's now noise filling in those gaps. And so for part one, we're going to do a Fourier transform so that we can understand where the magnitude, where it spikes up. And you can see here around 950 to 2500 hertz, the noise kind of spikes up. So what we're going to do is we're going to take that and we're going to filter it. So we're going to use a butter filter and basically cut out all those frequencies. It'll be a bandpass filter that cuts out that specific frequency, and that'll also cut out some of the original audio, so it's not going to sound 100% back the same, but it'll be filtered and there won't be as much noise. So here's what it sounds like.
Ice cream is delicious. Milk chocolate is not.
So obviously, I don't want to play the entire audio, but it's way more clear, but it's a little muffled because we lost some of those frequencies that we cut out from the noise. And so my methodology was to basically reduce the background noise. As I've already explained, I experimented with the Butterworth bandpass filter, and originally I had implemented, I think I'll show you here, the challenges and solution, yeah. So this Butterworth notch filter was a band stop filter, which allowed me to eliminate like smaller frequencies that were concentrated and adjust like the cutoff range. And then I used the fast Fourier analysis to compare the waveforms and do some performative matrix, the SNR and the MSE, to assess basically the effectiveness of how effective the cutting the noise out was. And then some challenges and solutions. I would say that it was a trial and error process, originally using the Gaussian filter, bandpass filter, and also even considered like a noise gating, but they didn't have enough, it didn't remove enough. I feel like the filter was still a lot of background noises. I tried adding like gentle noise gate to eliminate the low level background. And during the quieter parts of the audio, I tried, doing a bandpass filter for the certain moments that he isn't speaking, but I feel like that was a lot of filters. I just wanted to just do one filter that cuts out a specific frequency, but also inconsistent variable names, like testing different like versions. It caused a lot of like overlapping in the code and made the sound like doubling. Like I could hear it repeating itself, or depending on the, I guess just the noise that I use. So the notch filter was what I used with a certain frequency range, and it gave me the most clearest result. The ice cream clean file, and then we're gonna add our own custom noise. And for this, I just did a sine wave, which is just a straight one with one amplitude. That way it's just a consistent beep noise throughout the entire audio. We're going to add it to there, perform the analysis, and kind of the same exact way as the last one, but instead we're adding our own noise. So the original audio obviously sounds like this.
Ice cream is delicious. Milk chocolate is not.
And the original plus the sine noise is going to sound a little annoying.
Ice cream is delicious. Milk.
Anyways, there's the plot of both of them there, and then our noisy signal, I added just 18 hertz, just a random frequency. Did a fast Fourier transform, and obviously it was spiking up exactly where we thought it would, and I just subtracted a little less, subtracted a little bit more, just to kind of get rid of those leakage from the frequency. I'm not going to play the sine noise, you already heard it. So adding the custom noise, I added the original file, and I wanted to simulate a cleanable noise, so I was like, well, let me just add a sine wave, because that's something with just a specific frequency, and then I can just cut that right out. Pretty simple. So the band stop notch filter again, it kind of just had a width of 200 hertz to kind of give enough, I guess, depth into the frequency to cut it out. And I just used fourth order Butterworth. Anything lower was not providing me with any sound at all. So around fourth order was where I was provided the cleanest audio. And then, yeah, calculated the mean squared area and also the signal to noise ratio, SNR, using MATLAB's function. So some of the challenges, I guess, was the leakage. I was still hearing it, and that was the majority part. And I was like, well, let me just increase my sort of band filter so that I can actually filter out more of the lower and the higher ends of the frequency to cut everything out. And then trial and error, like tuning the filter, I guess, because it was just, at first the frequency was randomized, and I was like, well, let me just actually provide a frequency for it so that I can instantly cut it out. If I provide a random one at each time, it was hard to kind of have the program understand what frequency it's at and then cut that out specifically. So I was like, well, let me just define it as one frequency. Yeah, but despite all these challenges, I was still able to clean the reconstructed signal, and it helped me create a foundation for noise removal. So yeah, I think this one may be the filtered one.
Ice cream is delicious. Milk chocolate is not. I do not like chocolate.
So you can hear the no longer the noisy signal. You can hear in the background for that one. So yeah. And then for task 2, we were asked to create a pink noise. It wasn't asked to create a pink noise, but it was more of like generate a noise using like maybe Gaussian noise or just any sort of static noise that we want to take out. These are a little bit more challenging because it's not sort of one frequency. So I'll explain how I kind of went with this. But here's the noise that I chose. Some static. Right? Now we're going to do the fast Fourier transfer of the band limited pink noise. So my thought process was instead of having a static frequency that goes randomly over so many different frequencies, let's band limit the pink noise so that it's only spiking up at certain frequencies. Do a fast Fourier transform to figure out where those frequencies are, and then we can cut those out like we did before. Obviously, the noise sounds a little bit more muffled, but it's easier to work with. And then, so the original signal, you already know what it sounds like. And then this will be the original plus the band limited.
Ice cream is delicious. Milk chocolate is not. I do not like chocolate cake.
As you can hear, it's in the background there. And then this is our MSC and SNR, so we can kind of figure out a good decibel range would be like over 30 decibels. So I think 18 was the best that I could get, especially for being filtered. I was getting 5 decibels earlier, and I was doing some tweaking to figure that out. So this is with the filtered after the notch band filter.
Ice cream is delicious. Milk chocolate is not. I do not like chocolate cake.
So as you can hear, there's no more of that static in the background. So my methodology, as I was explaining throughout this PowerPoint or throughout this part, I wanted to, whenever I imported it, the signal was normalized, I guess, to kind of ensure that the amplitude remained at a certain range, so that way I can I don't worry about the clipping when I'm processing this audio. And I generated a full spectrum of pink noise, and I made sure that the noise matched the length of the original signal so that they can actually be added together. And then, since the noise spanned all frequencies, I did a third order bandpass filter and narrowed it down to 2000 to 2500 hertz, and scaled the noise to 60% of the original amplitude so that it would be easier to filter after isolating. And then I added a clean signal to create a pink noise contaminated version. I mean, obviously, so that I could have the sound. And then whenever I designed the Butterworth bandstop filter, I cut out those frequencies a little bit lower and a little bit higher, as you can tell, just 200 hertz above and below, so that I can cut out those frequencies that I added before, calculated the mean squared error and also the SNR to confirm my effectiveness on the noise removal process. Some of the challenges was, at first, I did a Gaussian noise, and I guess I could have done that before, but the reason I was like uncertain about the Gaussian noise is that the Gaussian noise had a like ton of frequencies that were hard to cut out. And so I was like, well, let me do a pink noise. It was a little bit more contained. And then I was like, well, let me do a band pass filter so that I can only pass a certain amount of frequencies to kind of basically contain that noise. And then when I add it, it's easier to cut it out. So also the audio quality, every time I filtered it earlier, I had to constantly fine tune it because it had really bad audio, and I was almost filtering all the noise out. So instead I slightened that band pass filter so that the noise was coming out at a sharper frequency so that I can cut out less of the noise. I also made the frequency a little higher than our speaking frequency, which is around 3 to 2000 hertz. And so I tried to kind of create the noise in the range that we're not speaking at, so it's easier to cut out without reducing the original audio and getting back what we have, storing the original audio. So yeah, that's everything. Thank you so much.